In this video, we're going to use what we've learned about solving right triangles and apply that knowledge to some real-world applications. In this example, we're going to find the angle of inclination. Suppose you were watching a rocket launch at Kennedy Space Center in Cape Canaveral, Florida. You're standing 4 kilometers away from the launch pad and have a camera mounted on a tripod that automatically tracks the rocket as the height increases after launch. After 30 seconds, the rocket is traveling 451 kilometers per hour and is 1.5 kilometers above the launch pad. What is the angle of inclination? In this figure, we've drawn a right triangle where the horizontal leg represents the distance from the camera to the launch pad, which is 4 kilometers, and the vertical leg represents the height of the rocket after 30 seconds, which is 1.5 kilometers. The hypotenuse of the triangle is the distance from the camera to the rocket when it's 1.5 kilometers high, and the angle of elevation, we've denoted theta, lies between the horizontal leg and the hypotenuse. So the two quantities that are known are the sides opposite and adjacent to our angle theta. And therefore, we can write tangent of theta equals 1.5 divided by 4. So to solve for theta, we'll use the inverse tangent function and write theta equals inverse tangent of the quantity 1.5 divided by 4. Now to make a little more sense of this value, let's use our calculator and obtain a decimal approximation. So let's make sure our calculator is in degree mode, and we're going to get that theta is approximately 20.6 degrees. In this example, we consider surveillance satellites. This problem states that a surveillance satellite circles Earth at a height h miles above the surface. Suppose that d is the distance, in miles, on the surface of Earth that can be observed from the satellite. In the given figure, we have a graphic of Earth. An arc on the surface of Earth of length d is subtended by an angle theta located in the center of Earth. The initial and terminal sides of theta are represented by the radius of Earth, which has a length of 3,960 miles. A bisector of theta is drawn from the center of Earth to the surface, cutting the arc of length d in half, and the bisector is extended up to the orbiting satellite that is a distance h above the surface of Earth. Two lines are drawn from the orbiting satellite to the endpoints of the arc of length d. For part A of this problem, we're asked to find an equation that relates the central angle theta in radians to the height h. So first, let's draw a right triangle that is composed of the angle theta over 2 that lies between one leg, represented by the radius of Earth, 3,960 miles, and a hypotenuse, which is the bisector of length 3,960 plus h. The length of the leg opposite angle theta over 2 is unknown and represents the distance from the satellite to the point on the surface of Earth at one end of the arc. Now on our right triangle, we know the length of the sides adjacent to angle theta over 2, and we know the hypotenuse. Therefore, we can use the cosine function and write cosine of the quantity theta over 2 equals 3,960 divided by the quantity 3,960 plus h. Therefore, we've written an equation that relates theta and h. Part B asks us to find an equation that relates the observable distance d and theta. This time, let's draw the arc of length d that is subtended by the angle theta. Again, the initial side and terminal sides of theta are represented by the radius of Earth of length 3,960 miles. Using the arc length formula, we can write S equals R times theta, and thus we have D equals 3,960 times theta. And keep in mind, in the arc length formula, theta must be in radians. So therefore, we have an equation that relates the observable distance D and theta. In part C, we're asked to find an equation that relates D and H. So to accomplish this, we're going to use the two equations we developed in parts A and B. Now remember, our equation in part A was cosine of the quantity theta over 2 equals 3,960 divided by the quantity 3,960 plus h. And the equation from part B was that d equals 3,960 times theta. Now, taking our second equation and solving for theta, we're going to have d divided by 3,960 equals theta. We're going to substitute this theta into our first equation. We get cosine of the quantity 1/2 times d divided by 3,960 equals 3,960 divided by the quantity 3,960 plus h. Simplifying inside the argument of the cosine function, we can write cosine of the quantity d divided by 7,920 equals 3,960 divided by the quantity 3,960 plus h. And this last equation is an equation that relates d and h. Part D of this problem says if the distance d is to be 2,500 miles, how high must the satellite orbit above Earth? Using the equation we just found in part C, we're going to need to solve for h. So multiplying both sides of the equation by the quantity 3,960 plus h, we have the equation, the quantity 3,960 plus h times cosine of the quantity d divided by 7,920 equals 3,960. Now dividing both sides by the cosine term, we have 3,960 plus h equals 3,960 divided by cosine of the quantity d divided by 7,920. So to solve for h, we're going to subtract 3,960 from both sides. So let's do that, and let's plug in the given information we have. So we have h equals 3,960 divided by cosine of the quantity 2,500 divided by 7,920, from which we subtract 3,960, which is approximately 205.8 miles. Therefore, the satellite will need to be 205.8 miles above the surface of the Earth for it to have an observable distance of 2,500 miles on the surface of the Earth. Now, real quick note that we need to be in radian mode on our calculator when we find the value of cosine of the quantity 2,500 divided by 7,920. Now, before we complete our next example, let's introduce the idea of bearing. In navigation and surveying, the direction or bearing from a point O to a point P equals the acute angle theta between the ray OP and the vertical line through O, which is the north-south line. So to illustrate this idea, we've drawn what looks like an XY coordinate grid. We're going to denote the positive y-axis as the direction north, the positive x-axis as east, the negative y-axis as south, and the negative x-axis as west. And we've labeled the origin as the point O. Our first illustration involves drawing a point labeled P1 that lies in quadrant 1, with a ray beginning at point O passing through P1. The ray is denoted as having an acute angle of 60 degrees between it and the north line. So the bearing from O to P1 is denoted as N 60 degrees E, which we read as north 60 degrees east. And this indicates that the bearing is 60 degrees east of north. The second illustration involves ray O P2, where the point P2 lies in quadrant 2. This ray is denoted as having an acute angle of 20 degrees between it and the north line. So its bearing from O to P2 is denoted as N 20 degrees W. And again, we read this as north 20 degrees west, and this indicates the bearing from O to P2 is an acute angle of 20 degrees west of north. The third illustration involves ray OP3, where P3 lies in quadrant 3. This ray is denoted as south 80 degrees west, again indicating the bearing from O to P3 is an acute angle of 80 degrees that is west of south. And finally, the last illustration involves a ray from O through point P4 that lies in quadrant 4. This has a bearing of south 30 degrees east because the ray OP4 is 30 degrees east of the south line. So now that we have an understanding of bearings, let's look at an example where we will find the bearing of a ship. In this problem, we are told that a ship exits the Panama Canal bearing south 60 degrees east. After traveling 1 mile, the ship turns 90 degrees towards the southwest. Maintaining the same speed, after traveling 5 miles, what is the bearing to the ship from the exit of the Panama Canal? So to begin solving this problem, let's visualize the scenario. We're going to draw a coordinate grid representing the directions of north, east, south, and west, and we'll put a point at the origin representing the exit of the Panama Canal. Now we draw a line segment in quadrant 4 representing the bearing of south 60 degrees east. I'm going to label the length of this line segment with the distance of 1 mile. I'm going to also label the angle between the line segment and the south line with a measure of 60 degrees. Now our line segment ends at a point we've labeled P that represents the location where the ship makes that 90-degree turn. Next, we draw a line segment of length 5 from point P to a point labeled Q. This line segment is perpendicular to the line segment of OP in a southwest direction. Now we draw a line segment OQ representing the bearing from the exit of the canal to the ship. The angle between the south line and the line segment OQ is denoted as X. In our diagram, we also note that the right triangle created by OP, PQ, and the hypotenuse OQ has an angle theta between OP and OQ. Therefore, we can write that theta will equal 60 degrees plus X, which means that theta minus 60 degrees equals X. And from a right triangle, we can say the tangent of theta equals 5 divided by 1, which means that theta equals inverse tangent of 5, which is approximately 78.7 degrees. So therefore, x equals 78.7 degrees minus 60 degrees, which is 18.7 degrees. So the bearing from the exit of the canal to the ship will be south 18.7 degrees west.